Hi. Today we're going to talk about the Lagrange error form for the remainder, sometimes called the Lagrange error bound, for the Taylor's theorem's remainder. Now, Taylor did a great job at coming up with how we can approximate any function using a polynomial, and we have our polynomial right here. The problem is we always want to know how accurate this is. Well, if it's an integral, we could use it would be plus the sum of the integral from b to infinity of a sub n, right? If it was alternating, right? If it was alternating, if it alternated, the remainder, the error, would be less than the next term. The problem is, well, what happens if we don't know what the next term is? Well, enter Lagrange, a Swiss mathematician. He did quite a bit for us. You'll see him a lot in linear algebra in college. Well, Lagrange said we could do, he says, well, looking at the Taylor polynomial to get the error, the remainder, that's my remainder right here, or the tail, what he said we can do is we can look at this value right up here, the part up here. This is a part that we won't be able to get always. We won't be able to know what the next term is. But what he said is, listen, your error is going to be the most it could be off. If you're looking for the most on an interval, like let's say you have an interval between C, your center, and X, what you want to find, you want to approximate. And let's say between what we're looking for and what we're trying to approximate, the function kind of goes up like this and then goes back down. We don't know exactly what it looks like. But we know somewhere in between there has to be a maximum value. It could be at an endpoint, we don't know. But this is my maximum value for the nth plus 1 derivative. So he said to get the maximum value, the nth plus 1 derivative. So what he said to do is to get the maximum value, we don't have to know what it is. We know it must exist somewhere. So to get the maximum error, I'm just going to look at over that interval of between where I'm centered at and what I'm trying to find is where is that maximum occurring. And we're going to plug that into the value for the nth plus 1 derivative, the next term. So it's still the same. We're still going to be less than the next term. The only difference is we're going to more approximate what the maximum value could be. Now that doesn't make too much sense, but once we take a look at an example, you'll kind of see, and it does kind of make a little bit more sense for us. So for part 1, we're going to write a third-degree Taylor polynomial about x equals 2. Now our polynomial, very simple, p sub n of x is the value of the derivative at c over n factorial times x minus c to the nth. Well, they kind of give it to me all here. So if I want to find my third-degree polynomial, I'm just going to write it out. This is 6 plus 4. Now remember, I'm going to go over 1 factorial. I'm going to have to do that. X minus 2. Minus 7. This is my second derivative. So over 2 factorial. X minus 2 squared. Plus 8, my third derivative, over 3 factorial. X minus 2 cubed. And there's my third-degree Taylor polynomial. Well, the next part they want me to do, use it to approximate f of 2.3. Well, I don't know what it is, but I can approximate it with my polynomial. And I write this out. 6 plus 4, that's just going to become 0.3 minus, 7 over 2 factorial times 0.3 squared plus 8 over 3 factorial times 0.3 cubed. Now, you type all that in your calculator, and what you get is 6.921. This is my approximation. The next question, part B, says, what's our error? How far off can we be? Well, this is where Lagrange comes in. Because Lagrange says, well, what if we don't know what the next term is? And that's what they're going to tell us. They don't normally tell you on the AP test, use Lagrange error bound, okay, on this approximation to find out how accurate we can be. Well, what Lagrange said is, very simple, is that our error, what Lagrange says is that the error of the nth term has to be less than or equal to, again, the next term, but we don't know what the next term is, so we have to kind of generate it. So it's going to be the value of the nth plus 1 term of z. Z's are unknown. Remember up here, z's are unknown. We don't know where that occurs, so we use z. So be very careful. Over n factorial times x minus c to the n plus 1. So I'm going to go ahead and do this. I'm going to write it all out to find my error of the third term. Now, why do I say less than or equal to? Because remember, we can include an endpoint here. We don't know where that maximum occurs, but we know it does occur. So if I plug all this in, my nth plus 1, sorry, that should be n plus 1 factorial on the bottom there. Sorry, most of you have already caught that. This should be 4 factorial. This is going to become x minus 2 to the n, up to the 4th, n plus 1. Now the problem is, what do I put here? Well, what goes here is my maximum value. So let's read the question. It says, the fourth derivative, the value of the fourth derivative satisfies this inequality. So this is right here our Lagrange error. This is saying the value of the fourth derivative cannot be greater than 9. So this is the maximum value of the fourth derivative of x. That's the maximum value of it. So that's telling me that the maximum value right here is going to become 9. And that's where I put the 9, right there. And I just simplify this. If I plug in my value, x in this case, so if I want to find the remainder at 2.3, I just now plug it all in. This becomes 9 over 4 factorial times, what's that? 0.3 to the 4th. And it's also absolute value because it's going to be positive error. Okay, it's going to be an absolute value for us. So when I solve this, we get the remainder at 2.3 has to be less than, and if I type all of this in my calculator right there, I'm going to type that in my calculator here. Enter. See, got that 6.921. You can see it. If I take 9 divided by, what's that? 24, and then multiply that by 0.3 to the 4th, I get 0.003. So we're saying our error has to be less than 0.003. This is my error, my maximum possible error right there. And now I want to find my interval. So, well, where does my actual value lie? We know how to do this. We're going to say that the error at 3 of 2.3 has to be between 0.003 and negative 0.003. So to get my actual value, remember this, it's going to be f of 2.3 minus my approximation, which we said was 6.921, has to be between negative 0.003 and 0.003. So my actual value has to be between, if I add it over, I get 6.924, and I get over here 6.918. And there's our estimation. The most important part right here, we're going to take a look more about that tomorrow too. We'll probably explain a little bit more of that in class. The next question, could the value equal 6.922? No. Or sorry, it is between, so yes. And that is because it falls in the interval. It falls in the interval. What about 6.927? No. It's outside the interval. So go to part 2, and we're going to go one more question. It won't take that long, I promise.